Hey everyone, let's start a new project. We'll cover YOLOv5 in 2 video episodes. To make it easy for beginners, we won't dive into theory, just show you how to implement it. Specifically, converting YOLOv5 models from desktop training to virtual machine models, to board-level deployment. Starting from scratch, we'll deploy the model onto the OrangePi 3588. This tutorial also works for the 3566 or other RK series development boards. There might be minor differences across different boards, which we'll cover step by step later. All files used in this video are available via the video link. Feel free to download them before watching. In this video, we'll train a YOLOv5 model to recognize digits, and deploy it onto our 3588 board. Before diving into the tutorial, let's preview the final result. As you can see, when the camera captures these digits, a bounding box appears over the corresponding number. The recognized digit is displayed in the bottom left corner of the box. The performance looks quite promising. This model isn't limited to digits. You can replace the dataset to recognize. For instance, it can recognize other fruits, vegetables, and similar objects. What specific objects it identifies depends entirely on your dataset. Speaking of datasets, we'll start by explaining how to create your own. First, capture images of the objects you want to recognize, and place them in the folder provided via the link I shared, specifically within the Images folder. Next, download a software tool called LabelImag. I'll post the installer in the comments section, or you can find it online yourself. Open the software, and select Open Folder here to choose the folder containing your images. Next, return to the LabelIm directory, and navigate to a subfolder named Data. Inside, you'll find a TXT file, listing the target categories for recognition. Here, we'll change it to 1 and 2, so the subsequent video only recognizes these 2 digits. If you need to identify other objects, replace these entries with the names of your target objects. After modifying, return to our software. Here, select the location to save the modified labels. Save it to this folder. Here, I hold down W and drag the box. Select the number 1 with the box. After releasing, you'll see a box pop up. Here, we assign the corresponding label to our selected box. Here, I selected 1, so my label is set to 1. Using the same method, we assign labels to the subsequent numbers. Note, labels should tightly adhere to the target for optimal results. Avoid making them too long or wide. Crucially, prevent mislabeling, as this will impact future accuracy. If the target appears tilted, minimize overlapping other digits. Ensure complete coverage of the target, while minimizing inclusion of surrounding objects. After labeling an image, press Ctrl+S to save the labels. Press D to switch to the next image for annotation. Since labeling typically involves hundreds or more images, it is a labor-intensive process. Be meticulous to avoid errors or omissions. After labeling, you can find the labeled data in this folder. The labels are in XML format. Next, divide the labeled data into training and test sets. The training set provides features for machine learning, so it can make predictions when encountering unknown images later. The test set is used to evaluate how well our trained model performs, and whether it remains effective in new environments. Since the code below contains relative paths, open pycharm within this folder. Locate the .py file here and run it directly. This script will automatically split our dataset into training and test sets. We can see 4 txt files generated in this folder. These are our test and training sets. Next, locate this file mentioned in the video. Change the class on line 7. The object type here, to our own categories. For example, I'm using digits. Note, although the final model handles all 10 digits, 0 to 9, I'm only demonstrating digits 1 and 2 here. We continue to call out. Later, you'll need to replace all paths with those on your own computer. Here, I held down Ctrl+F and replaced them all at once. One more detail to note. At line 66, if your images are in JPG format, no changes are needed. If your images are in PNG format, change the file extension to PNG. After completing all steps, click Run. You'll see the txt label file appear in the Labels folder. After completing these steps, return to the main YOLOv5 directory. Locate the data folder. Open the file named myvoc. Again, replace the paths for trend and value with your local computer paths. Change the NC value, representing the number of classes, to 2. This is because my demonstration only uses the numbers 1 and 2. Then adjust the categories below to 1 and 2 accordingly. Next, locate the YOLOv5s.yaml file in the Models folder. Change the NC number of target classes to 2 here, matching the value we just set. This completes the preparatory steps. Now, open a terminal in the master directory. Copy the following command sequence and paste it into your command line. You'll see numerous parameters listed here. I'll share the meanings of these parameters in a Word document. Feel free to download it if you're interested. Here, I'll briefly introduce just 2. First is the batch size. This value determines how many images the machine processes per training round. Higher values mean faster training, provided you have sufficient memory. A larger batch size is generally better. Second is the epoch parameter, which defines the number of training cycles. Typically, 100 to 200 iterations suffice. Too few iterations may result in insufficient accuracy, while excessive iterations risk overfitting, making the model overly rigid. Minor image variations could then cause recognition failures. Press Enter to initiate training. Observe the 50 iteration process, which takes several minutes to over 10 minutes. I'll fast forward through this part. Here we see the final results. Our training accuracy is quite high. After training completes, we see a generated Runs folder. Opening it reveals multiple folders starting with EXP. Each training session creates one such folder. My latest one is EXP5, this is our current training result. Inside, numerous charts assist in analyzing training outcomes. As for the model we just trained, it's actually stored in this Weights folder. Inside, there are 2 models. One saved from the last training session, and another representing what the machine considers the best trained model. Now that we have the model, let's first run inference on our computer to check its accuracy. This time, under the YOLOv5 master directory, find the detect.py file. You'll see many lines here. These are all parameters. We only need to focus on the first few. For instance, the first parameter requires importing our model file. Here we use the best.pt model obtained from the recent training. The second parameter, source, means we need to provide an image for the computer to perform inference and see if it can correctly detect and bound our target object. The third parameter, data, requires importing our configuration file, myvoc.yaml. So here we also copy the path of this file and paste it after the default section. Similarly, we randomly select an image and paste its path after source. We also copy best.pt to the weights field. Once everything is set up, simply click Run. Afterward, within the Runs folder, you'll find a generated detect folder containing the inference results. As seen here, it accurately identified the digits 1 and 2, with probabilities of 0.87 and 0.79. Since we only trained for 50 epochs, and the dataset wasn't particularly large, this result is still somewhat acceptable. After training is complete, we need to deploy this model onto our OrangePi. This requires two steps: first converting the PT model to ONNX, then converting it to an RKNNN model. To convert PT to ONNX, we first navigate to YOLO.py and locate the forward function. Then we comment it out, as this forward function is for training purposes. Find the commented out forward function above, and uncomment it. This forward function is used when converting PT to ONNX. Specifically, training uses one forward function, while model conversion uses another forward function. If we forget to switch here, either training won't proceed normally, or the converted model's network structure will be flawed. Next, copy the command string from Word into our command line and press Enter to run it. We can then locate the newly converted ONNX model in this directory. We've now successfully converted the PT model to ONNX. As for converting ONNX to RKNNN next, we'll complete that process on the virtual machine.